Hello, Washington Liberty Chemistry students. This is your Unit 6 lesson on Introduction to the Mole. So we're used to the idea of 1 dozen equaling 12 of something. It's a convenient grouping for a lot of items in our lives. For example, it's very convenient for eggs or donuts. Somebody says, go out and get a dozen donuts. We know we're getting 12 donuts. Someone says, I need 24 eggs. That means I need to get 2 dozen eggs. Very convenient. A package that we can pick up, bring home, is useful for our consumption of eggs or donuts. Now, a dozen is a grouping that's good for very large things, but it's not very convenient for atoms or molecules. These are particles that are extremely small, and even if we had 12 atoms or molecules in front of us, we wouldn't be able to even see that with our eyes. So we need a convenient grouping for atoms and molecules so that we can work with them and know how many of them we have. So just like 1 dozen equals 12, we have a unit called the mole. 1 mole equals this number, 6.02 times 10 to the 23rd. Again, it's just a number. Just like 1 dozen equals 12, 1 mole equals this really large number, 6.02 times 10 to the 23rd. Now this is convenient for atoms and molecules because it gives us an amount of atoms and molecules that we can actually see and work with. For example, in the picture over here, we have 1 mole of each one of these elements. A mole of carbon, a mole of sulfur, a mole of copper, a mole of mercury, and a mole of iron. And in each one of these samples, we have 6.02 times 10 to the 23rd atoms of those particular elements. Just like we would have in a dozen eggs, 12 eggs. In this case, in this carbon, for example, in this 1 mole of carbon, we have 6.02 times 10 to the 23rd atoms of carbon, and it's an amount that we can work with. So this is such an important number, and we're going to ask that you memorize it, that it actually has a special name. It's called Avogadro's number, and it's named in honor of Italian chemist Amedeo Avogadro, who is pictured right here. So you are going to need to know and memorize that number. Now this is such a big number because atoms are so small. And I'm going to give you some examples. If we blew up atoms to the size of standard soft drink cans, an Avogadro's number of standard soft drink cans would cover the surface of the Earth to a depth of 200 miles. So again, as we've talked about in previous units, atoms are tiny. If you had an Avogadro's number of unpopped popcorn kernels, so just blow them up to popcorn kernel size, not to soft drink size, and spread them across the United States, the country would be covered in popcorn to a depth of over 9 miles. And if you were able to count atoms at a rate of 10 million per second, it would take 2 billion years to count the atoms in 1 mole. So, in other words, this is a really convenient thing so that I don't have to go to the grocery store and count out my eggs, the 12 eggs. I don't have to count out my atoms if I know I have a mole of them. Now, so 1 mole is always the same number of small particles. And I just want to emphasize that just like we can use a dozen with either eggs or donuts, different kinds of food items are convenient in a dozen. I use moles for small particles. And we've learned in previous unit 2 types of very small particles. Atoms, which are kind of the singular, and the most fundamental particle. It's the fundamental particle of most elements, but as we recall, there are 7 elements that are diatomic. And so we could also count moles of diatomic molecules here, because they're also small. Or if we have a compound like water, again, it's in a molecule form. We could have a mole of water molecules or a mole of other kinds of atoms. So let's just go through this again. So 1 mole of helium atoms would be 6.02 times 10 to the 23rd helium atoms. A lot of them, but a number of them where we could actually work with that amount of helium gas. Here's hydrogen. In this case, we would have a mole of hydrogen molecules, H2. So 6.02 times 10 to the 23rd hydrogen molecules. Now, just to be clear about this, that would be how many molecules. We'd actually have twice as many atoms because there are 2 atoms in every molecule of hydrogen. But we could say if we had a mole of hydrogen, H2, we'd have 6.02 times 10 to the 23rd H2 molecules. Now we also could have a mole of water, 6.02 times 10 to the 23rd water molecules. Now again, water's made up of 3 atoms. We'd have 3 times as many atoms there, but we would have 1 mole of, if you were counting out, water molecules, if you had models of water molecules and started counting them, of course it would take you a long time, but a mole would be 6.02 times 10 to the 23rd water molecules. And then finally, just going back to that fundamental atom, very convenient, 1 mole of lithium is 6.02 times 10 to the 23rd lithium atoms. And actually, we can work with that amount. So you have to understand this is just another unit that you have to memorize, and to convert between moles and number of particles, you just have to use dimensional analysis. So it does not have to be terrifying. Okay, so just to remind you, we can use dimensional analysis to convert between moles and particles. And the particles that we are converting between are either atoms or molecules. The conversion factor we will use is 1 mole equals 6.02 times 10 to the 23rd particles. And again, remember, we use these conversion factors in one of the 2 ways, and we want the units to line up diagonally so we can cancel out. Whatever's on top is what we're going for. So we're going to try some of these, okay? And yes, you're required on your test to show us with dimensional analysis. So here's an example. Please write it down. Try it out. How many atoms of lithium are in 3.50 moles of lithium? And again, 1 mole equals 6.02 times 10 to the 23rd particles. And in this case, the particle we're going to use is atoms. So here's our given. We have 3.50 moles. That's how we abbreviate moles. And what we're going to is atoms. And here's our T-chart. We're now going to arrange the conversion factor so we can cancel diagonally and have whatever unit we want, which is atoms, on top. So you might pause the video, put it in, see if you can figure it out, but I'm going to show you the answer now. So here we go. We would arrange it. So again, 1 mole equals 6.02 times 10 to the 23rd particles. And in this case, we're talking about atoms. So 3.5 moles times 6.02, and the moles cancel. We're left with atoms, is 2.11 times 10 to the 24th atoms of lithium. There you go. All right, let's try another one. This time, let's start with atoms. So how many moles of lithium are in 3.35 times 10 to the 24th atoms of lithium? Again, our particle here is atoms, and that's what we're going to be saying. 1 mole is 6.02 times 10 to the 23rd atoms, just like we could say 1 dozen is 12 eggs or 1 dozen is 12 donuts. This time the particle we're using is atoms. So 3.35 times 10 to the 24th atoms. How would you arrange the conversion factor? You want to cancel atoms and be left with moles. So again, you cancel atoms. So this is going to be a division. Now, be careful how you put this in your calculator, but I would urge you to think a little bit about what magnitude the number should be. You have to worry about order of operation or know how to use your exponent key. But you could also just look at canceling out some of these exponents. Like 10 to the 23rd would cancel this out to 10 to the 1st. So really this is just 33.5 divided by 6.02. Makes sense. It would be about 5.56. So 5.56 moles. All right, next. This time, I want you to set the whole thing up yourself. We've got 5.61 moles of iron, and we want to know how many atoms that would be. Pause the video, set up the T-chart, remember your conversion factor, and then I'm going to show you the answer right now. So we had 5.61 moles. We would arrange the conversion factor so mole is on the bottom and atoms is on the top. We cancel moles, so it's just 5.61 times 6.02, which would be 3.38 times 10 to the 24th atoms of iron. Okay? All right, let's try one more. This time, our particle is going to be molecules, but it doesn't change anything. Molecules are also small. All right, so our particle this time is a molecule. So 1 mole is going to equal 6.02 times 10 to the 23rd molecules of water. And we want to know how many moles of water that is. So again, pause the video, see if you can set this up, and I'm going to show you the answer now. So again, 9.31 times 10 to the 24th was our given. Here is, again, it was molecules. So again, our conversion factor, the particle we're using now is molecules. 1 mole is 6.02 times 10 to the 23rd molecules, which would be 15.5 moles of H2O. Now, again, the idea is you could cancel units, and you could cancel 10 to the 23rd and 10 to the 24th. So this is really just 93.1 divided by 6.02, and that answer makes sense. Now, I want to emphasize something. This is how many molecules of water we have. If I were to ask you how many atoms were in this, you would need to realize that water has 3 atoms. So there are 3 times as many atoms in this sample. But in terms of whole molecules, this is what we have, 15.5 moles of H2O. So just a little chemistry humor to end. What do you get when you cut an avocado into 6.02 times 10 to the 23rd pieces? Think about it. Chemistry Cat will tell you the answer now. And the answer is you'll get guacamole. Ha, ha, ha. You know, a lot of pieces, mole, guaca, get it? Avocado. If you don't, ask your friend or ask your teacher. This has been your lesson on Introduction to the Mole.